get started by talking about possibly the simplest example of these types of novel kind of phenomena that we want to study, and that is non-relativistic diffusion. So the idea behind that is basically that we have some sort of conserved quantity, a conserved current. Think about the electric current or something like that. That current basically I can write as, well, I want to sort of use for notation, but it's not necessary for this problem here. I want to decompose it into a zero component, which I call the density, could be charge density, and the actual sort of free current. And this current is fulfilling an equation that looks like that. So it's just the conservation of the current. Why is it the conservation of the current? Well, if we take a volume integral dv of this equation, we get dv dtn is minus dv gradient of j. Then, since this is an integral over the volume, we can pull out the time derivative, so we get dt dvn is equal to something on the right-hand side where we have the total volume integral over divergence. That's just a surface integral. If the volume is infinitely large and our current sort of goes to zero sufficiently far at infinity, the right-hand side here just is zero. And that just means that we have some conserved charge Q. That's the volume integral over the density, which is conserved. So its time derivative is just zero. Okay. Conserved charge Q. Now, this conserved charge Q is basically the building block of what we're sort of going to study. It's a Lorentz scalar. So we have one Lorentz scalar. And I choose to sort of use this zero component of the current, the charge density, to sort of do that. And that will be the thing that I want to sort of build up a theory for how that charge density basically behaves if you have an arbitrary situation. So let's think about a situation where we have a charge density that in initial state has some distribution. Okay, so you make up a charge distribution that has some maximum here and a minimum over there, and in between sort of is distributed in some form. And the question we want to ask is, if we switch on time, how does the charge density behave? Okay, so what's the dynamics of the charge density? How does it sort of evolve as time goes on? And what I'll sort of try to build up is an effective field theory for this evolution of the charge, the dynamics of this charge as a function of time.
Oh, can you explain why you call it Lorentz scalar? It's a number divided by volume, and volume is not Lorentz scalar.
Right, so then the actual Lorentz scalar is of course the charge. But yes, the charge Q is the Lorentz scalar, but the charge density is the associated sort of quantity. It's not a vector. That's essentially my main point. Yeah. Thank you. So since that is sort of the main quantity that I want to sort of build my sort of setup for, the quantity that I have to sort of say something about is the other entry in my current here, the current density J. And what I want to do is I want to write J in terms of an effective field theory approach. I want to write J as a function of N, okay? Because that's the only quantity that sort of I have. It's the fundamental building block. Now, in doing so, I can write down basically constructions out of this N, and I will have to say what are the symmetries that I sort of impose for this construction, because depending on the symmetries I have, I will get a different theory. Okay? Here, basically, I will assume Galilean invariance, isotropy on the rotations in 3 space-time dimensions, and I will assume parity. Okay? If you change any of those assumptions, the theory that you get out at the end will change. But you have to say something about what the symmetries of the system are that you're studying. So if we do that, then in the sort of framework of effective field theory, we can sort of study the simplest case possibly, which is that okay, how do we write down a theory of the current density in terms of J? So J is a vector, N is a scalar. So the 0th order solution would be J is just 0 with a vector. That's not a very clever sort of theory, but we can write it down. Okay, so if we do this, then we can look at the current conservation equation up here, and what we get is dTn is 0. That is basically just static charge sitting there and nothing is moving. Okay? Of course, you may say this is a stupid example, and I agree with you. The reason that I give this example is that when we go to fluid dynamics, hydrodynamics, it's this 0th order approximation that will give us an interesting theory, namely the Euler equations, which have a very broad applicability. But just for this case, it's not very useful. Okay? But you can study it in principle. Let's do something more interesting. Let's go beyond sort of first order. What is sort of the first order gradient correction that we can write down for this current J? And I'm taking suggestions from the audience. Gradient of n, yes. Gradient of n. And since there can be a proportionality factor in between the two of them, I'll call this proportionality factor minus d. The minus is convention. And note that this d here, in principle, can be a function of the number density n. We haven't said anything about what that can be. We only said that the current J to first order ingredients is proportional to the first order gradient of n. Okay, so far so good. If we plug this J back into the current conservation equation, what we get is that dTn minus, in principle, that's a function of the number density n. However, for the discussion here, I will assume it to be just a constant, simply because it simplifies the math of writing it down. But in principle, there's nothing that stops us from keeping the full general function of n here. It's just that the equations get longer. So I will assume d to be a constant just for the purpose of this lecture. So if I do that, then the gradient of J, the divergence of J, the divergence I can pull through this thing that I now assume to be constant, and I have a Laplacian here, so that I get the Laplacian n is 0, and that equation here is nothing else but the well-known diffusion equation. Okay? So there are several things that one should remark about this. The first thing that I remark about this is that obviously this diffusion equation we have sort of derived just from the fact that we said that we want to sort of expand in gradients. We want to expand the underlying dynamics in terms of gradients. So we have said nothing about that. What's underlying here are electrons that sort of bump into each other and they sort of scatter, have scattering rates and things like that. So from that point of view, since we haven't said that, and we've also not said that, okay, we're studying a black hole, but the horizon is charged and it's sort of doing an ADS-CFT-like dynamics, this equation here is universal. Okay? Does not depend on the microphysics. Just depends on the symmetries and pretty much nothing else. It will be the same equation at low momenta, whether you have electrons scattering with each other or you're studying black holes in ADS-CFT, they will have both this particular equation. So the form of the equation is universal. However, the transport coefficient is diffusion constant d. That is something that I cannot calculate from this effective field theory framework because I haven't said what thing it is that I'm actually studying. So this, if you want, so number or function, that will depend on the microphysics, and it will be different whether you have in your mind electrons scattering weakly in a sort of metal, or whether you have an ADS-CFT plasma where you don't even know what the quasi-particle excitations are or whether there are any. Okay? So the d will depend on the system, the form of the equation will not. Now, question to the audience. Is that diffusion equation exact or not? And if not, what are corrections? Yes? Say again? you can have corrections. So this is not an exact equation. We used a truncated first order gradient to sort of get to this equation. There can be higher order corrections. So what I want to do next is I want to sort of look at these higher order corrections and see where these leads us. Okay? Let's see. I want to study higher order diffusion. So in my counting, this was order 0, where the current is just no gradients. There are no structures to be converted down, so it's just 0. This was first order gradients because we had one gradient of the density here. So what are second order corrections that we can write down? I will need help from the audience for that. The audience needs some coffee. Yeah. It's not that hard. What do we have at our disposal? We have a space-like gradient and maybe some other gradient. Suggestions, please. There are no suggestions. I will call on different people to sort of make suggestions. Then is the question, do I start with the students first, or do I start with the full professors first? The students, okay, good. Please, students. Yes. Nabla n dot nabla n. Okay. Nabla n. Oh, I'm sorry. No, that's not a vector. That doesn't work. We had a suggestion, which was nabla n dot nabla n, but that's a scalar. That doesn't work. Nabla n partial Tn. Yes, that is one possible structure, but another structure would just be dt nabla n. Okay, so then we have formally two gradients, a time gradient and a space gradient, the second order gradients acting on n, but it's not unique. Okay, we could write a different term, which you just said, which would be nabla n times dtn. That's of the same order, but yeah, so both of those sort of come in. They're of the same order. So both of these would come in with some coefficients. Let's call this alpha and this one beta or something like that. And they're perfectly fine, except that if we look back at our sort of equation for the conservation of the current, which is exact, okay, so we should have noticed this one is exact. It tells us that if you're doing a gradient expansion, we can use this exact equation to sort of relate time and space gradients. Put differently, time gradients and space gradients are not independent. This equation tells us how they are linked. And in particular, we can use this equation to replace any time dependence of n by a space gradients of j. So if we do this here, this term here is synonymous with having alpha gradient of, then we have a dtn. The dtn is minus j. That's minus the gradient of j, but the j we can sort of replace by its lower version over here. So we get minus plus d gradient n. So long story short, this first order in time and first order in space gradient is the same as the gradient of the Laplacian of n up to some constant alpha prime. So to reiterate, there's an ambiguity in how you count space and time gradients. And for the diffusion equation, you can replace first order time gradients by 2 powers of space gradients. Okay. Let's sort of make an identification that says that for the diffusion equation, 1 power in time counts as 2 powers of space. And from the point of view of the derivative expansion, how we set up our theory, these are equally valid. Okay, we can write down one or the other, or we can write down a mixture between of them. We can't decide. But if we want to have some scheme where we sort of want to write only independent forms, we have to sort of make a choice whether we use one or the other. The standard choice is to say that you always replace all time derivatives by the corresponding space derivatives. But it's a choice. So if we do that, we find that, strictly speaking, there is no second order diffusion in the sense that there are no terms of second order space gradients of the number density that we can write down. But really what it sort of boils down to is that this is really a third order term, that we have something like this structure, or, as was pointed out before, something that involves a nonlinear term that sort of couples the gradient of n together with the Laplace of n or something. And that's a lesson that we'll recover when we go to fluid dynamics. It has sort of similar sort of features, except that in fluid dynamics we'll have a sort of ambiguity that has first order time with first order space derivatives. But we'll get there. So here we have first order time is equal to second order space. Now, the question that I sort of want to ask now is, okay, so fine, so you get these terms here. Is that all? Okay, so are these, we know that we have two possible contributions, one which is linear, the other one which is nonlinear. We know that we can write them as time and space derivatives. But is that really everything, or should we sort of think about other terms of contributions that crop up when we think about corrections to usual diffusion? Can anybody think about other things that we have not talked about at all at this level? And for a change, I will, unless there are any volunteers, I will ask the full professors first. Yes, my hint is that usually when we have moving electric charges, there are things that we like to include in the description. Yes, so basically what we usually have, if you have a moving electric charge, it usually induces an electric and magnetic field. So there are fields that sort of crop up naturally in the description of moving electric charges. Okay? So moving charges usually come together with E and M fields. In this case, E and M fields, well, I mean, if you think about charge, that's really what's happened. But in this sort of construction, you would even get sort of fields if we thought about n not being as the charge density, but also as the mass density, okay? Then they would be fictitious in some sense. But they crop up in the distribution, meaning that besides my Lorentz scalar here, there are things that we like to call sources that we usually describe in terms of well, a vector potential A mu. And these sources here, they sort of enter the description of the effective field theory just as our other building blocks. So now we discover that, okay, we not only have this Lorentz scalar n here, but we also have these associated sources. So they have gradients too. In particular, there are the electric and magnetic fields, and they are both, let me call it, first order in the source A. So they sort of crop up in this description also when we sort of want to talk about the corrections to the diffusion equation. So basically what I'm saying is that already at this first order level here, where we wrote down the gradient of the number density, we should have included a different term here that comes from the fact that if you have a moving charge, we naturally sort of want to include E and B fields. So basically that then leads to a sort of modified first order current that sort of looks like the one we had. And then we have, in addition, contributions such as the electric field, which is first order gradients, and the magnetic fields. But then you sort of think back to what I said before, it all depends on the symmetries. So I secretly said that I want to sort of assume parity as the symmetry of the system. The magnetic field doesn't, or is odd under parity flips. So that means that by symmetry, contributions of the magnetic field are forbidden here, except of course if you say you don't want to have parity as a symmetry, if you want to sort of study chiral fluids that sort of break parity explicitly, then you should include a term of the magnetic field in this description. So that's an explicit example how the symmetries that you assume modify the sort of theory that you get when you build up these effective field theory. Let me maybe sort of write it like this. Let me call it sigma prime B, but I'll cross it out because of parity. And these fields sort of are naturally things that you should include in your description, and they will modify the diffusion equation. Okay. So we can plug it into the exact formulation of the current here, and we'll get a sort of equation that sort of includes essentially Ohm's theorem as well as the other sort of building blocks that we've talked about. It's possible to say that I'm not really interested in the effect of the electric fields. Maybe sort of the system that I'm interested in is sort of an insulator, or there's some other reason why I say that, okay, the fields are not interesting, but it's nevertheless natural to include them in the derivation, even if that's not the case you're finally interested in. And the reason is subtle. The reason is not that if for some reason you say your electric fields in the actual application you're interested in is important, even though it's very small, it has to do with correlation functions. Okay? So this is sort of more for the experts in the audience, but there is a relation between the sort of, these things are called transport coefficients, the diffusion constant and the electric conductivity sigma. And that sort of is a deep consequence of essentially fluctuation dissipation theorem. Okay? How you get this out in terms of this EFT construction is actually pretty straightforward. Let me sort of quickly do that over here. So let's say we want to calculate correlation functions, such as the 2-point correlation function of the current. There are two methods of doing that. One of the methods is that we use the usual linear response. So we ignore the electric field. We're not interested in that. We do set up there, sort of do a small perturbation of the Hamiltonian, and then the 2-point correlation function will have something to do with this diffusion constant here, and maybe the rate of change that I'm sort of doing by perturbation. And we'll find that this 2-point correlation function in Fourier space sort of behaves like this diffusion constant times omega. It cannot depend on sigma because we set E to be 0 from the very start. So you get that this correlation function sort of looks like this. The alternative method is to say that, oh, I know how these things look like. I have sources, A mu. The sources coupled to my current in the partition function. So there's a partition function, we sort of call it, well, there's an action S that has a term d for x or whatever, J mu A mu. So I can calculate correlation functions of the current by doing a variational derivative with respect to the sources. So basically I do derivatives with respect to A mu. If I do this on the current, since that's the only part that depends on A mu, this one doesn't. This will only pick up contributions from sigma. And you find that essentially the sort of 2-point correlation function sort of depends on sigma in a specific way. So you find that basically this depends on sigma, omega, and I think there's usually some sort of static susceptibility chi in here. And then you say, okay, but this correlation function should be the same no matter how I calculate it. And from this you get a relation that says V is chi sigma, which is the well-known Einstein relation. So to reiterate, in this whole setup, we have never said anything about, we have electrons that bump into each other and we sort of directly calculate this diffusion constant and electric conductivity. We don't know them, but we can find relations between these constants just from, if you want to, the consistency of the theory. And this is one example of this, okay? That says that even though we don't know D, we don't know sigma, we know they have to fulfill this particular relation. for any system. Okay? There's no exception to this. Well, if we have the symmetries, that sort of thing. And that's also something that we'll sort of see when we go to full-blown hydrodynamics. It sort of follows the same ideas essentially. Okay, so far so good. So we have a sort of framework that sort of lets us write down a theory in terms of a gradient expansion, and we discover sort of certain elements of it, such as that there's this duality between the time and the space derivatives, and that for consistency, we have to include these associated sources to the whatever object we're studying. In this case, to the current, there are these sources AJ, basically. So they give corrections to this diffusion equation. So we might now sort of say, okay, what does the dynamics sort of look like? Can we sort of say something about how sort of really this distribution of charge density that we talked about at the beginning evolves as a function of that? It's the static susceptibility, the second derivative of the pressure with respect to the chemical potential. Wait, maybe there are some questions up to this point. I'm already pretty fast, so there are not enough questions from the audience. Let's see.
This business with the variation to A was pretty quick and pretty fast.
Right. Yes. I'm sorry. We can do that in a little bit more detail. I sort of said this is more for the experts, but it's not something that's hard to sort of understand. So sort of clearly again. So correlation functions, for instance, J, n numbers of these J's are usually sort of calculated in terms of varying the log of the partition function Z with respect to the associated sources in the action. In our case, since the action is proportional to the integral of A mu J mu, that's basically the source that I have to derive.
What happens with the A0?
Right. So if these are J alpha, beta, zeta, then we have the alpha, A beta, A zeta. Endpoint correlation functions are just.
We have to take here by just putting on the expression.
For instance, exactly. Yes, yes, yes. So that's one way of calculating this correlation function. That's the one that is most often, I would say, used in quantum field theory. But there is nothing wrong with sort of the canonical formulation that says that you sort of add something to your Hamiltonian. It's a small perturbation, and you basically just calculate the Green's function of that operator over here. And that Green's function basically is the two-point correlation function of your current. That will give us the first. Other questions up to this? Yeah. The W is the omega, the Fourier frequency. I sort of was getting a little bit ahead of myself. It's if you transform time into Fourier space, that's the frequency that you get. That's usually the way that you express this correlation functions. In this case, so I truncate them at first order ingredients, which is just omega. You can, but they will not come in at leading order in omega. They will come in as omega squared. So yes, there will be contributions, but at the first order level, it's first order, so it only cares about first order transport. It's actually kind of tricky because once you sort of have the full theory, there's no reason to believe that this gradient expansion is analytic. And in fact, you find that there are non-analytic terms, so-called long-time tails, that screw up these purely power-like expansion. And then you have to rethink very hard what your sort of higher order sort of gradient terms really mean. But we'll get to that when we talk about the series in more detail. Yes.
When you have the order transfer, do you mean that this expectation value of transfer
Here and here, right. So before we had it, my sort of, however you want to call it, third order term, there was a term that was dn Laplace n, and both of those are meant, here n always is the expectation value of it. It's a 1-point function. Because you're sort of taking the expectation value first, you're expanding in the expectation value of the current. And you're looking at non-data dynamics of that. You basically sort of project out correlation functions. And to get back, so basically what I'm doing is I'm screwing up correlations. And in order to get back the correlations, I would have to introduce, for instance, a noise field.
I mean, what you're saying is this in classical theory, yes. In classical theory,
That's right. It is the expectation value of these things squared. Because I'm doing classical description, I'm throwing away correlation functions. It's precisely what. It's exactly the classical limit. But I'm screwing up correlation functions if I do that. Yes. And in order to get them back, there's a way to do this. But so this breaks FDT. Fluctuation dissipation theory. It's only the dissipation part of the fluctuation dissipation theory. And I can repair it, but right now I'm not doing that. I'm just thinking about classical applications. And it's a simple example. But this term is there. Other questions? Okay, good. So if there are no other questions, then let me talk a little bit about the sort of outcome of this. So if we take the diffusion equation again, I can sort of copy it over. Minus d Laplace and d0. Again, I sort of am negligent about the electric field for now. Let me just assume that it's very small, or that I'm doing mass diffusion or something like this. I want to sort of know what this diffusion equation now tells me about the actual evolution of the charge. And the easiest way to get at this is to say that we want to go to Fourier space. We're going to have n is proportional to, let me see, what are my conventions here? Minus I omega t plus I p dot x and twiddle. And twiddle is the Fourier transform of my charge density. We plug this into this equation here, and we find that this is equal to minus I omega and twiddle minus d, which I sort of take to be constant, times the derivative of n. The derivative brings down an ik. So basically we get squared, we get twice this ik, so we get minus k squared. We have plus k squared and twiddle is 0. I can pull out the n twiddle in Fourier space, and I get minus I omega plus dk squared times n twiddle is 0. This equation has two solutions. One of them is interesting, the other one is not. The uninteresting one is to say that, okay, my charge density is just 0. That trivially fulfills the diffusion equation. Not very interesting. The more interesting one is to say that the thing that's multiplying my charge density is 0, and that's what we call the dispersion relation. And it's giving us a relation between, if you want, so the frequency and the wave number. So in this case, it says that I omega is equal to dk squared. It is sort of imaginary, so that means that omega here is just minus I dk squared. I can plug this back into my solution here, and it says that n, now let me restate the space-time parts here, is equal to E. I have minus I omega, so minus I times minus I is minus 1. So I get minus d k squared t plus I k dot x times my n twiddle here. That's my solution for the diffusion equation. And what that tells us is that, so we can prepare some initial condition of this n twiddling Fourier space. Okay, so it's the same as preparing it in usual space. We just take the Fourier transform of this. And then it says that the time evolution of this initial state is governed by this solution here. This solution here has an exponential factor, e to the minus d k squared t, which says that A, it's exponentially falling in time, and B, it's falling the faster the higher k's, okay, because it comes in with e to the minus d k squared. So the higher k modes damp out much faster, the lower k modes don't damp out so fast, but they still damp out. And yes, there is some sort of real time to this, okay, so there can be sort of real sort of evolution of this system. So, so far so good. And there's, again, nothing wrong with this. It's a very successful example of an equation in physics. However, because we want to study relativistic fluid dynamics in the next lecture, or maybe sort of even at the end of this lecture, let me point out one maybe not so nice thing about the diffusion equation. The thing that's not so nice about the diffusion equation is that if I look at this dispersion relation, I can calculate formally some sort of group speed. Okay, so define the group speed Vg as the absolute value of omega because it's imaginary by dk. If I do this, I find that this is equal to 2dk. Okay. Yes. I have what?
Oh, sorry.
You have, I mixed up a sign? Okay, maybe we should take votes about signs, okay? I'm not particularly good about signs, so it is easily possible that I screw up signs here and there. So please, yeah, check. If there's something that seems odd, let's just let me know. Okay, so this group speed here sort of looks at like that. Also, because eventually I want to talk about relativistic systems, I've set the speed of light to 1, so I'm using units where the speed of light is 1. And that means that this group speed here, I can plot this as a function of the wave number. And it looks like this, Vg as a function of k, linear, right? So somewhere here is 1. So the group speed here happily goes through 1, sort of keeps on growing wherever it's unbounded. And again, okay, this is non-relativistic diffusion, so maybe we shouldn't be worried about it because, well, it's non-relativistic. But nevertheless, people have worried about this. Famously, there was a guy called James Clerk Maxwell who worried about this because he said, okay, this equation here says that the speed of propagation exceeds the speed of light. That's not good. Okay? So he was worried about this and sort of said, okay, this equation can't be right. Okay, it violates one of the things that we measure. Can't be that they have a rod and sort of prepare a temperature profile, and the temperature profile sort of goes out instantaneously fast. That violates special relativity. It wasn't called that by that time, but still. So clearly this diffusion equation can't be right. It needs to be corrected. And that's one of the sort of hints, if you want to, that it should be correct. Now, we have talked about corrections to the diffusion equation, right? We have talked about higher order corrections. And we said that, okay, yeah, there are corrections that come in, for instance, a third order in spatial gradients. So let's see, maybe those help in sort of solving the problem. Okay. Unless there's some questions. Okay, so I talked about third order confusion. No, yes. Third order confusion. Yes. And I said it can be written down as a term that sort of involves. Maybe let's use the other term. Let's use the term that's linear because it's easier to Fourier transform. So this was a term where I have one gradient acting on the Laplace of n. Okay, so this term is third order in gradients. It contributes to the current, and it will give a correction to the diffusion equation. Let's see if that maybe counts. Okay. So if we do this thing, we plug it into the exact equation for the current conservation, we get something that, let's see, gradient J. So we have dTn plus the first term here gives us minus d plus n. That was that term over here. And now we have this additional term here, minus alpha. And now we get two Laplaces acting on n. Okay. Again, we can try to Fourier transform this equation. I omega plus k squared minus alpha k4 times infinity 0. Is that right? Does school have any signs? Do we need more coffee? Cookies, maybe. So we get a dispersion relation from this, and the dispersion relation looks like this. It's minus I e k squared plus I alpha k4. Okay. And as a consequence, if this was our first order theory, we can calculate the group speed for this, and it's not better. Okay. Let's see. Vg something like 2dk minus 4 alpha k cubed. Maybe. It looks like this. Group goes negative, or rather, okay, the absolute value of that. Maybe something like this. So it doesn't help. Okay, so it still has a very strange behavior, in particular at high wavelength. So you would say, okay, no, higher order contributions really don't help. Okay. But then you remember that, oh, wait a minute, there was this thing where we could sort of use either two space derivatives or one time derivative. So let's just for fun try the other realization of exactly the same term. Okay. So we sort of write down V3 alt. And instead of having this term here, let me sort of replace these Laplace of n by one time derivative. And I get something that has the gradient and one time derivative of n. And basically, I want to sort of, it's also maybe a minus d there. Shouldn't be going too fast. Let me sort of just say this is proportional to. First, I replace the two time derivatives by one, the two space derivatives by one time derivative. And then I say, oh, but the first time derivative here, writing this down so we kept it in a box, it was over there, dTn plus gradient of j is 0. So the first order time derivative I can replace by the total divergence of j. So I can write this also as proportional to the gradient of j times the overall constant, and I'll choose the overall constant as equal to minus tau. Yes, I think it should be good. So I have an alternative sort of, wait a minute, no, what did I want to do? That's not what I wanted to do. What I want to do is, what did I want to do? Not do that. Do something different. I want to, right. What I want to do is I want to sort of write this as, write it as dt gradient of n. And now I can sort of go back and say, oh, but my leading order first order current J1 was just minus d gradient n. So really what I have over here, gradient n up to a factor of d is just the same as the current itself. So really what I want to do is I want to write J3 alt simply as dtj times a different sort of constant, which I call tau. Okay. So it may have gotten a little bit confusing, but basically what I'm doing is what I sort of said earlier, is that there's an ambiguity between the time and the space derivatives, and I can sort of use this to sort of reshuffle this, which is all the same in the effective field theory counting, but maybe sort of gives a different result for the equation of motion. So that's basically where I'm going. Okay.
J is J1.
Yes. Yes. That's right. So if I do this, then what does the Coherent conservation now look like? Let's do that. I think I can do that over here. So we have this equation over there, and then we have J being minus D gradient N, and then minus tau gradient J, gradient dt, dtj. So that's sort of the alternative version of this current here. So now we have two equations. We transform both of them into Fourier space. Okay. So if I transform this into Fourier space, I get a J twiddle, which is minus d I k n twiddle. Now I have to think. I just deleted my conventions. I think this I do e to the minus I omega, so this is plus I omega tau J twiddle. That's the Fourier transform of this. And the Fourier transform of that is minus I omega n twiddle plus I k J twiddle is 0. Okay. Yeah.
Is that J1 or just J?
Good question. It's just J. So we sort of wrote down something that was exact to this third order framework. It included the J1, but it also included these higher order things. So instead of really sort of saying which one it is, I just say that that's J, and I sort of use it effectively as a dynamic variable. And that's precisely where the trick or the difference comes from. So let us write down one more thing and then try to sort of give a more informative answer to your question. So what this equation here tells us is that now we have J on both sides. That's different than what we had before. So I can sort of put this on the other side and find that J twiddle times 1 minus I omega tau equal to minus I d k n twiddle, or J twiddle is minus I d k n twiddle over 1 minus I omega tau. Take this, plug it into this equation over here, and you find minus I omega n twiddle. So now we have plus ik times this, plus ik times minus ik is plus d k squared n twiddle over 1 minus 1 minus I omega tau. And what you should see is that, okay, all the third order, if you want to higher order effects, come in this parameter tau here that I sort of snuck in here, right? That's where all the third order things go. So if I set this to 0, I should get back to my original diffusion equation. So if I forget about this thing here because tau is 0, this is just 1, then I should get back to what I had over there. So I'll call this first order, this third order. And I find, yeah, okay, minus I omega n, dk squared n, fine. Okay, I get back to the limit of where I was before if I sort of throw away the terms that I added. Okay? But let's look at the dispersion relation of this alternative formulation. And what you find is that you have minus I omega plus dk squared over 1 minus I omega tau 0. That means that I get some sort of quadratic equation for my dispersion relation. So if I bring this to the other side, I should get I omega times 1 minus I omega tau is equal to d a squared. And okay, this is a second order solution, second order equation. We can solve this. Maybe even I can solve this. I'm sure you can solve this. So let me start try to solve it over here. So the first term here on the left-hand side should be I omega times minus omega is omega squared tau. Then we have plus I omega. And then we have minus d k squared, 0. That's the, okay, I see people nodding, so maybe I can completely screw this up. So then we get omega squared plus I omega over tau minus d k squared over tau is 0. Omega 1, 2 is plus minus, sorry, is 1 I over minus I over 2t times minus 1 over 2 tau squared plus d k squared over tau. I don't see people nodding. That's probably a bad sign. What did I do wrong if I did something wrong? Say what's the? You liked it, okay. So we should have a Facebook page, I guess. Should I get more likes than dislikes? It's fine. Okay, so let's assume that I did this right. And then what this is telling us is that, okay, we have a funny equation here, which if you stare at it, makes sense. And in particular, if you take the limit where we take this equation and we say k is much more smaller than, it's small, then we can expand this spheroid for ignoring this term here. So basically we get this plus minus I over 2 tau again. So we get that omega 1, 2 as one solution where just add these two together. So we get minus I over tau. And the other one is where I sort of have the other sign, so it comes in with a plus. It cancels the previous factor here, and everything that remains is basically that thing. So if you do this slowly, it should be something like that I have minus I over 2 omega. And both of those have corrections at higher point.
Why don't you have to take the square root?
Oh, I did. I expanded for small k. It's just it's an illustration of this is the exact result. I'm expanding for small k basically because originally I did this gradient expansion. So this is valid for small gradients, which is valid for small k. So let's just stare at this for small k for now. Okay. And what you find is that, okay, for small k, we get this guy here, which, oh, yeah, it's the same as the one that we started with. Okay, that's good. Okay, if we hadn't recovered that, something very bad would have happened. Okay, so whatever we did, in addition to usual diffusion, gave us back usual diffusion in some limit. But look, there's a second one here. It looks kind of strange. Okay, so what is that? Okay, so if you look back at our dispersion relation, where we said that n twiddle, or n is e to the minus I omega t plus I k dot x, and in twiddle, this says now we have to replace omega by minus I over tau. So in this particular case, we get a solution n. It stays like e to the minus t over tau plus something. There's no k. There's some other sort of behavior. But it's there, okay? So we find some funny results, okay? In particular, this sort of second solution that we get here, it doesn't vanish as k goes to 0, so it can't be a usual diffusion pole. So it's not a transport or hydrodynamic sort of excitation. It's some sort of other non-hydrodynamic feature. It also means that for this second thing, even for small k, the frequency of that excitation does not go to 0. It goes to a constant value if tau, this parameter tau, is constant. Right. I basically said that, okay, we have a diffusion pole, which is the analogous thing as a hydrodynamic excitation.
So when you translate it to hydrodynamics, you will see similar.
Exactly. So I should have called it non-diffusion, Paul. It's a non-diffusion. It's a non-diffusion feature. And it occurs at a frequency that's not small for small k, so it really doesn't look like anything that we're used to from usual diffusion. Okay? And even though I'm not talking about hydrodynamics, I will call this thing a non-hydrodynamic excitation. So it's coming out of this. Yeah. This one. This one is the diffusion. This one is the usual sort of diffusion pool that we sort of found in usual diffusion, and this is some other thing, a non-something something. Okay. It's a bad word, anyways. Non-hydrodynamic. Come on. Anyways, so it's something else. Okay, it's not usual diffusion. But the nice thing about this is that if that is our dispersion relation, if we look now at the group velocity of this thing, it will be bounded by this term here. And you can check that, well, you can first of all check that the group velocity is bounded, and you can also show that the Green's function is bounded. So I claim that this theory here, this is perfectly causal. For tau over d is larger than some critical number. So the speed is always finite as long as tau is finite, this parameter tau. And for a particular ratio of these two, this critical value will actually be less than the speed of light. So this seems like, doesn't sound like physics, right? I mean, we start with a very nicely defined scheme. We sort of laid out this gradient expansion, higher order gradients, and we found that, okay, there's trouble, but fine, it was non-relativistic diffusion, so why bother anyways? But then came Maxwell, and Maxwell said, yeah, you should really look at this more closely. So we sort of looked at other sort of formulations of the same theory. We're just traded terms in our counting scheme, okay? So instead of saying, okay, this is second order in time, second order space, we said it's first order in time. And then sort of, as was remarked before, so it is this sort of crucial sort of magic where not saying that, okay, this is the first order current, but we said it's the same thing that appears on the left-hand side, okay? So what we've secretly done under the hood, and you can also see this in this equation over there, is that we have actually sort of resummed an infinite number of spatial gradient terms. You can see that by looking at this expression for the current and expanding out in small tau. So you find that, okay, this will be a sum that will involve omega tau to some power times the original IED k squared, okay? So that's what we've done. We've sort of not taken third order diffusion or fifth order diffusion, we have taken infinite order diffusion and just sort of resummed everything in a nicely compact form such that we get this effective sort of treatment that introduces the parameter tau. Where was it again? Here. This parameter tau. And then suddenly the theory that we get out, at least is causal, but it has these additional features. Okay, so it sort of goes to our usual diffusion equation at the limit of small wave number, at least part of it, but it has an extra sort of degree of freedom. Its group speed is bounded. Yeah, all of this basically happens at momenta that are comparatively large to what we sort of set up. Yes. Right. So basically, let me see. Critical basically is you sort of calculate the actual group speed. You have to take a derivative of the square root, which I can't do here in my lecture, in my head. And then you look at where this is 1, and this is what d over tau or tau over d critical is.
So tau over d larger than the group speed remains below speed of light, otherwise it still goes above.
Yes. And again, keep in mind that what we're really doing is non-relativistic diffusion, so you shouldn't be bothered about most of these things, but exactly the same things will happen once we talk about hydro in the next lecture.
Sorry, you think that Romatschke, I think this correctly, this is k squared multiplying d over tau, and this is k squared, right? Romatschke, your group velocity is just square root of d over tau.
Yeah, so this is 1.
If this is speed of light.
Thank you.
You said something about being slower than the speed of light. Maybe I misunderstood.
No. So you're right that omega goes like square root of d over tau times k. So square root of d over tau is the group speed. So if the inverse of this is larger than 1, then the group speed is smaller than 1, right?
You said something that the round is not right.
No, it is the speed of light. Yes. Yeah, causality sort of means the speed of light. Okay, I have one more thing that I'd like to sort of.
Before we move elsewhere,
Yes.
we use the word resummation. We want to actually show that resummation explicitly. Is that what you get by expanding 1 over 1 minus I omega tau into power series?
Yes. So take whatever. Okay, where was it?
Second line.
Yes, this one here. So here you have the coefficients here are actually 1, n is 0 to infinity. These are an infinite number of terms that you have to resum in order to get this version.
And you can generate that by doing what you did before.
Yes.
And keeping the difference between different orders by adding one
Yes.
orders.
Right. I can go back and say that, okay, each of these corresponds to certain time derivatives of my original sort of fields. And I can write down precisely those terms that sort of resum to this series. Yes, that's explicitly possible. They are not all the terms that are there, but it's a particular subclass of the terms that are going on. I was looking for one reference that I wanted to. There it is. So note that this group velocity business is kind of a little bit hand-wavy because, okay, the group velocity sort of tells us something, but if you have, in particular, imaginary dispersion relations where you have damping, then the group velocity itself is not really a proof of how sort of whether there's a violation of causality. Really, what you have to do is calculate the Green's function of the corresponding operator and show that really sort of, well, first of all, that this violates causality and this actually restores the causality. And it's a classic calculation. It doesn't fit in my lecture, but for those of you who have time at their hands, I would recommend as an exercise, show that the Green's function for star, the star is this equation here, together with that equation over there. So this implies causal behavior for this particular bound of ratio of transport coefficients. And in case you get stuck, so I first want you to sort of try to do this. In case you get stuck, this is worked out in the appendix A of 09G02.366, which shows you explicitly there's a Green's function. The Green's function only has support in the causal region. The causal region is dictated by this ratio. And it involves, if I remember correctly, some Bessel functions. So it's not a completely trivial calculation, well, unless you sort of know these things by heart. Good. So fine. So there are some lessons that sort of come out of this. And we'll sort of, again, as an expose, we find these things again when we talk about full-blown hydrodynamics, except in hydrodynamics, there are much more indices that we have to deal with. There are different modes. But the physics remains exactly this, okay? If you do a particular resummation, you can change the dispersion relation such that the outcome is causal, but you have, as a price to pay, you find additional modes that are not the modes that you started out with. These are non-dot-dot-dot modes, where dot-dot-dot will be hydro in the next lecture, but it's probably diffusion or something like this. Okay. There's one more thing that, if you stare at this dispersion relation for a little bit, might seem interesting or odd to you. Can anybody guess what I'm talking about? let me give you a hint. So originally, sort of, we talked about the dispersion relation for diffusion. That was just this diffusive mode. Okay, has just imaginary damping, or just imaginary omega, which is just damping of your setup. Look at that equation. You find that if the square root here has two terms, right? I mean, one of them is positive, the other one is negative. At small k, which is the expansion that we did, we always were in the regime where this dominates over that. But there's a critical wave number k at which suddenly the sign flips. And then suddenly you get something that looks like a propagating diffusion mode. Still has damping, but has a propagating part. And at this point, you might say, okay, this is really crazy, right? I mean, there's no notion this could be real because we started out sort of this small k expansion, and this critical k is way outside of the regime of applicability. And then you talk to people and they say, oh yeah, we noticed this happens in water. Okay, there's something water which have shear waves. Shear waves have exactly this diffusion character. After above some critical wave number, they turn into propagating modes. We notice. It's perfectly fine. So, wow, but how did we miss this? Okay, but even though sort of the whole sort of setup was meant to sort of be in the effective field theory framework at low momentum, you seem to get a lot of qualitative physics right that you didn't really deserve to. Okay, but that's just magic. I'll just let this thing.
Is this accidental and qualitative, or is this theoretically true?
So on a qualitative level, it's real. Quantitatively, I don't know. I have never really studied water. Usually, I study much more tricky things to measure in the lab. So if somebody has a sort of idea how to measure this in the quark-gluon plasma, I would be very interested. But yeah, I don't know. I have some references. People looked at this, but I don't know how quantitatively well this actually is. Okay, let's see if there's some more questions on the diffusion part of things, because next I want to sort of maybe prepare the stage for the actual hydrodynamic lecture. We'll sort of go through the similar exercise again, but there are many more things that we have to be careful with. So that's the next stage. Okay, then I think, yes. Oh, sure. I mean, at this level, all I've done is to say, okay, I have one formulation, I have another formulation, I try both and see which one looks good. Yeah, totally. So at this level, it's if you want, so very hand wavy. There's nothing. I mean, if I didn't have the knowledge that this sort of makes sense from an experimental point of view, there would be no justification that I could give that this is the right thing. And indeed, if you had asked me 10 years ago, I would say, yeah, it doesn't make any sense. You shouldn't really trust this. Now I say, okay, you shouldn't really trust it, but it gives the right result. So, yeah. Okay. What will I keep? Yeah, let's keep this. Right. Yes. Yes. That's correct. Yes. Yes. So that's perfectly right. So the setup that I've chosen is an effective field theory setup, in which case it is valid, or is meant to be valid, for small wave numbers. So the fact that it violates causality is in principle not an invalidation of the scheme. I mean, it just happens, and it was not meant to sort of work at high wave numbers, in particular not at infinitely high wave numbers. Nevertheless, if you want to study, well, I mean, from a basically what you want to sort of have is you want to have some way of potentially having a UV completion of your theory. That's really sort of what we are thinking about. And again, for many purposes that might not be necessary, it's kind of necessary if you really think about relativistic fluids, we should talk about next, simply because if you have a violation of causality, it means that you're not free to give initial data at time 0, because violation of causality means there are modes that move backwards in time. So if you were specifying your initial condition, you move forward, there are these modes that travel backward in time. They manifest themselves as exponentially growing things. So it basically means your computer codes crash. So there's a practical reason for that. Even though from a principal point of view, you could always say, well, if I had an analytic solution, I could always project out these high K modes and sort of look at just the low K stuff, and that would be perfectly fine. But good luck trying to do that with fully blown nonlinear hydro. So that's sort of the notion for the context. So, okay, so for diffusion, let's just reiterate what we did. So we said that, okay, there is a scalar charge Q, which is conserved. Then we sort of write down, so the building block, EFT building block there's this number density n, and basically what we do is we write down J as a derivative expansion of n. Let me sort of formally write this down here, where I only use odd powers in spatial gradients because the even powers are absent if I sort of use the fact that every time derivative I can replace by 2 space derivatives. Okay. We found that at least at the first order level, we also want to sort of have sources, the electromagnetic potential, which means that we include E and D fields, and these first arise first order diffusion, J1, where we have to include these guys. And we found a number of other things that we alluded to in the last hours. So let me talk about hydrodynamics in the same framework. So there, hydrodynamics is basically built out as an effective field theory of the conserved quantities, which are energy and momentum. So we can sort of lump these together as a 4 momentum P mu, and then that means that instead of having a scalar quantity, we have a 4 vector quantity, which is the conserved quantity that we want to sort of use. And as such, I want to sort of use the same idea as I did in the diffusion equation, which is that I want to sort of write down an effective field theory in terms of these building blocks. And it would be perfectly fine to sort of use what I just wrote down here as building blocks. For historic reason, however, I chose to sort of write this as such that I sort of take out, if you want, so the energy. And then what I have here is the momentum density divided by the energy, which formally has mass dimension 0. So this is kind of more like a dimensionless vector. So long story short, instead of using the 4 momentum here, I use the energy density and a 4 vector u mu, which is normalized in a particular way to sort of have 4 degrees of freedom that have exactly the same character. Okay? So again, this is for historical reasons, but it has one quantity, the energy density, that corresponds to the energy per volume. And then instead of having the momentum density, I have the 4 vector, which is basically a 4 vector that's sort of normalized such that I have only 3 independent components. So these are my building blocks. Again, mostly plus. I can try to change the metric signature.
Just don't ask us for correcting signs.
Yes, yes, yes. I can try to change the metric signature on the fly. I will probably sort of get myself screwed up. I will, yeah. We'll see, and we'll talk about science if there's one.
I have a question here. That battery is relatively low. Should I close the machine before something bad happens?
No, nothing bad will happen. We'll just run out of battery. But I'm almost done anyways.
So
Let's just leave it there. If it dies, it dies. And so if we sort of use these building blocks, essentially the thing that we have to ask ourselves, well, what is a good quantity that we want to use this EFT for? And obviously, over here, the thing that we were interested in is the equation of motion of the current. So since we're talking about energy momentum here, the corresponding equation of motion that we're interested in is the conservation of energy momentum. That's given by the conservation equation of the energy momentum tensor. So this is the same as the current conservation equation. These are two exact equations. And we want to build up the theory by making a sort of setup for the constituents of this object. So we want to write down d mu nu in terms of epsilon, u mu, and gradients.
And now W is a covariant.
Yes, we'll get to that. Yeah. I mean, so far I haven't said anything about that. So this is, it could be a usual partial derivative so far.
But it's not spatially transferred.
No, it's just a usual derivative. So fine. So we can basically play exactly the same game as before. Okay, so here we said, okay, we have our current. Can we write down structures that involve the building block and gradient such that we get the same structure as this current here? Well, here we have an energy momentum tensor, which is a symmetric rank 2 Lorentz tensor. So symmetry is Lorentz symmetry. And we want to write this in terms of epsilon and u mu, where epsilon is a scalar and u mu is a vector. What can I write down? Question to the audience. Everybody knows that. If you don't know it, then Uli will be on you. We have to ask full professors. Maybe I should ask in the back.
No,
Dick, what is the energy momentum tensor? No, I'm asking Dick. I'm asking Dick. I want to write down a second order rank 2 tensor out of scalar and one vector. What can I write down? Yes. So it has to be symmetric. So you have two of these u's, they are vectors, and you have an epsilon. The thing, of course, is that similar to what we had before, it can be epsilon, but it could also be 2 epsilon, or it can be pretty much any function of epsilon that I can write down there. But maybe there's a second thing that I can write down. G is bad. Let's call it F2. We can write on a metric tensor. Why would you write on a metric tensor, right? I mean, so we are interested maybe in fluid dynamics for the gluon plasma, which is in flat space. So why would you write on a metric tensor? Well, there are 2 reasons, or really only one reason. Think about what we had before, where we said, okay, moving charges typically imply that we have sources, electric fields, and these sources naturally come from the fact that in the action before x, you couple your current to some gauge field A mu. Well, now we are doing moving energy and momentum that naturally sort of couples to gravitational waves, and indeed the action naturally couples G mu nu to the metric tensor G mu nu. So really, by analogy, you have to sort of include the metric tensor. The same way that moving charges, diffusion equations sort of come hand in hand with electric and magnetic fields, relativistic hydrodynamics naturally comes with gravity switched on. Of course, you can
introduce this term long before they were thinking
Right, and that was not an EFT framework. So, I mean, it's not, I'm not saying that this is sort of suddenly a new term that appears. I'm saying that it naturally sort of appears in the construction that you should think of these energy momentum tensor living in curved spacetime. And of course, you can always sort of say, well, I'm not interested in the effect of gravity. Let me sort of project back to flat space. And then this metric tensor is just Minkowski. But for the constructions, it's important because it will give you Einstein relations. And if you sort of start from flat space, you will never see those.
And if you use curvilinear coordinates in flat space, you still have to remove it.
Right. Yes. But basically, my argument is that if you follow the principle that we sort of lined out for the diffusion equation, the natural thing to do is to include curvature of spacetime, meaning a non-trivial metric tensor. And we can always sort of go back and project back to flat spacetime at the end, but for the derivation, it's natural to include it, and otherwise we'll miss terms if we don't. So that's the idea.
Also, this actually appears in the normalization of the.
In here, yes, that's of course true. So once I sort of said that, okay, there's a metric tensor in here, of course the metric tensor appears everywhere. It's here and there. Yeah, this one. Yes. Let me see, I think I'm out of time. Is that right? Okay, then let me sort of thank you for today's audience and the attention, and we'll continue tomorrow.
There's a question.
Yes.
So I guess you had an expression for correlation of currents,
yes.
correlators in terms of functional derivatives. The question is that how is that general expression obtained again, and why will we have a general expression for current correlation but not for the current itself? That's the question.
Okay, so I think I understand the first part of the question. I'm not sure if I understand the second part of the question. So what I had on the board is that there is a partition function which is some integral over some fields, we call it d phi in quantum field theory, which has an action, and this action here includes a term that looks like this. It's J mu A mu, because that's the way that I couple. That's the way how I couple to the current in the quantum field theories, by introducing a source in. So if I do that, then I can calculate basically dz by dA1, dA2, whatever. And this, and I sort of evaluate this at A is 0 in the end. And if I do that, then if I sort of do a functional derivative, this will bring down J's for every time I derive with respect to one of the A's. So I will get an expectation value of J1, J2, and so on, if I sort of calculate this functional differential. I don't think I understood the other.
So the question was originally about why would we have a general expression for current correlators but not for the current itself? I guess you can say you can't have a matrix element for the current itself.
Right, I think we had a general, I mean, part of the construction was indeed to include the A's in the construction for a current. So we have the A's in the current too. I'm not sure if I'm answering the question.
I guess if you take this first derivative, just take derivatives as once on the
yes.
ACL, you will get current itself, not current correlator, current itself.
If you take one derivative on the A field?
So right now you have multiple derivatives on the A field.
Yes.
If you just take one.
Oh, yes. Well, yeah, okay. No, I've got it. I'm sorry. Yes, sure. If you take only one, then you could just get the expectation value of the current. That's right. Yes. Yeah, sorry. I only drank half my coffee.
Okay. Is it okay if I announce that if people have more questions, they can send you
Oh,
emails?
totally. Yes. Yeah, let's do that.
And I also forgot to say in the introduction that Paul wrote a book on the subject that he's discussing, and this has everything that he is talking about here and much more, I suppose.
Yeah.
So I have no idea. I don't think you can get through this in 5 lectures.
No, I will not get through these 5 lectures. It has stuff in that I once knew but don't know anymore. So if you really want to know what's going on, read the book, because I might have forgotten about it.